receive Professor Antonio Cadilhe today. Professor Cadilhe got his bachelor's at Universidade do Porto in 1990. Then he got a PhD at Clarkson University in New York State in 1995. And he did a series of postdocs in the US and Brazil, Iowa State from 1997 to 1999. And in Los Alamos in New Mexico from 2007 to 2012. And then he did a postdoc at UFMG from 2014 to 2017. And today he's going to talk to us about novel polymer diffusive behavior on more realistic surfaces. Professor Cadilhe, thank you very much for accepting the invitation, and the microphone is yours.
Thank you very much. I'm really appreciate to have this opportunity to describe a bit of the work that I've been doing on polymers. It's not the only subject I've been working over my career, but this is the one that I worked for quite some time, and some novel diffusive behavior has been studied. And I will show some of it, not all of it, in this talk. So one thing that I want to just remind everybody is that how long I have been working with polymers. And from this is my first publication, and it was in 1989. And by the time I had to perform these simulations on a mainframe computer, not a typical nowadays computer, it's a mainframe. So on this computer, it took 18 months of CPU time to get the leading confluence exponent, which is the second most relevant one. So that was by the time when I was still an undergraduate student. Then, why study polymers and what polymers represent? Polymers are very complex molecules, but they have units that will be repeated again and again along the sequence. Let's say a linear polymer. So for that, I have these beads that describe what is a monomer. But the monomer here, we have 8 of them. And it can be something quite complex, like in the group I'm working with Professor Vivian. It's an effective representation. So I have the monomer, and the monomer it's just a representation of all these atoms that we are seeing here in brackets for chitosan. So it's a very complex molecule, and would be impossible to do simulations, extended ones, if we were not reducing the degrees of freedom in some way. And at the end, coming up with a more effective representation. And on the right side, we could see a possible state of the polymer inside the box. And this is for work on the bulk. And that's what we are looking at. So polymers, they have to, since we are working at some temperature, they have to diffuse. And early studies, there were considering no excluded volume interaction. So it's a random walk, and the gyration radius will basically scale as n to n squared times ni to the power ni, and this is 1/4. So if we wanted to include the possibility that monomers, they cannot just cross themselves, and therefore there is excluded volume present, then one can define a radius again in terms of the number of monomers, n, and it will, in a mean field approximation, being given by the expression on the right for the exponent. So d over here is the spatial dimension, and this can be found on the book of the Jean, a very good classical book on the subject. Then, if on the other hand, if the polymer is on some liquid, and therefore there is some dissipation or thermalization of the polymer, or it is, and we'll see that also on a substrate, one can consider that the polymer is thermalized in all degrees of freedom with equal weight. So therefore, this leads to a Langevin type argument that should go as 1 over the mass of the system. And since all monomers are equal, it's basically 1 over n. So that's basically the argument for the dependence of the diffusion coefficient in this case. And we'll see that more of that in a moment. On the other hand, these are what I'm labeling as traditional studies. In a sense, I also studied that in that initial paper, but it was not for diffusion on that one, but including the gyration radius. That was the main goal, and some other quantities that no longer are that relevant these days. But by the time it was. The other part that I want to move on, that's what I consider more relevant, is diffusion on crystalline substrates and also deposition of polymers on substrates, possibly including nanoparticles. And we are studying this type of problems because people have been studying polymers for some decades, and simulations have included, for example, smooth substrates. Smooth substrates are very simple to simulate. On the other hand, they also have problems. One of them is that shifting the polymer along the substrate does not change energy. So there is no energy barrier for that. And that can be a problem once we use also molecular dynamic simulations, because that is can build some behavior that is not expected to be present let's consider here, for example, this substrate that I have. And so on the horizontal, we have the potential, the energy, the potential energy, and upwards is the distance relatively to the top of the substrate. So if I do that, there is a point that I may consider that there will be a minimum of the energy, and so the polymer would basically move around that point. Since the substrate is a wall, it's basically infinite. The energy, it cannot be penetrated. So there is here a distance that can be only moving upwards. And the energy is not very large because it's only dependent on the position of the monomer along that particular direction. And if the polymer displaces horizontally in whatever direction, there is no change in energy, and this can be a problem. On the other hand, this type of studies are very interesting because one can have polymers that are in the solution, and at some temperature, they will basically start absorbing to the wall, and other times at higher temperatures, they will not. So there is what is called a transition temperature, where the polymer would absorb to the surface. And above that temperature, it will basically evaporate, and on average, there would not be polymers attached to it for a long time. But for temperatures below that transition temperature, there will be always polymers attached to the substrate. And from a microscopic point of view, these polymers, they don't have to be attached to the substrate all the time. But one polymer can leave, there will be another one that will get to the same spot and occupy the substrate. So these are the type of problems that one could want to study, but with the presence of a substrate that is crystalline, in the sense that I'm putting here. It's a crystal, in this case, along a face-centric cubic substrate along the 100 orientation, and therefore we have the polymer. But now every monomer, when it moves to a neighboring equilibrium position, it has to overcome an energy barrier that is built because the substrate is no longer flat. And so it's no longer a flat energy landscape. Even with that in mind, we still have to will obtain a behavior that is basically of 1/n in terms of, or Langevin type result as 1/n. And we see here that I basically define some length scale to be the equilibrium distance, and some length scale that basically also defines the equilibrium distance between substrate particles. Of course, at a given temperature, this length scale will vary because of thermal dilation, and therefore there is some effect of expansion. On the other hand, to compute the diffusion coefficient, we can use what is called Einstein Relation. Basically, we follow the center of mass over time relative to some initial time. This is, in fact, the case for if we just want to observe the polymer for a long time over a crystalline substrate without any impurity or obstacle present in it, and the polymer will also not, say, dissolve or evaporate from the substrate. So if the absorption is good and there is no obstacles, we should find what is usually expected, that this fluctuation should be linear in time. And the constant is the diffusion coefficient is D. So this is what we are going to use all the time. But if we have different conditions, we might be or have to be more careful to deal with time-dependent cases. But we'll see that in a moment. So basically what I did so far was to divide two main cases. What I called more the traditional studies, mainly in the bulk, and now moving into studies that are more recent, that the field is being shifting towards, and diffusion on crystalline substrates. I did some of this work when I was at UFMG, and so I did their study with two models, and I included even a third one for comparison. The third one is the smooth, analytically smooth surface, the one that it's a flat energy landscape. And the two other cases are described or depicted below in the following sense. One is isotropic in the sense that if a monomer basically interacts with many of the substrate particles on the substrate, let's say the monomer is a sphere or has a geometrical sphere-like appearance, or a disk, or many particles interacting with the substrate particles, and all those particles are basically attached or absorbing the monomer to the substrate. It does have a very different behavior from a monomer that has some structure. I'm not even caring much about that structure. What I did was, it could be one or two atoms in the monomer that will be basically attached to the substrate, and all the others too far away to interact with it. But 1, 2, 3, it's as good as one from an effective point of view. And from an effective point of view, then there is only one particle interacting. I don't care for the remaining of the particles, and therefore I call this case anisotropic. So here, in this last case, the size of the monomer is not going to make a difference in terms of the binding energy of the monomer with the substrate. In the other case, the binding energy is proportional to its size. It's not it's proportional to a volume or to a surface. And that's a very different behavior from one case or the other. I considered mainly in the study just the surface. But it could be also the volume. So if I do that, now I have to consider what are the simplest interactions that I should consider with a polymer. Well, one is that the monomer and substrate, they should attract between themselves, and therefore I introduce a simple Lennard-Jones potential. Why doing that? Because I could be doing a very good energy or force calculations, but that is not useful when I want to see a polymer moving by a distance of its size. So we have to observe diffusion, we have to move polymers by distance or let them displace by distance comparable with the size of the polymer. So trying to look to very good quality potentials at short distance, it's not that relevant. So that's the main argument for an effective representation. If we are just looking for diffusion, and that's what I'm trying to study. Of course, other problems, they have to be studied in a different context. So the other part that is relevant for the polymer is that we should not let the monomers go very far away. So the potential should diverge, not allow monomers to displace very far away from each other, because there must be bonding between them. And so we have a chain that has to be maintained. Finally, the other component is that if I have one monomer, say, in one extremity, and I have the other monomer on the other extremity, and they find themselves later at some point in time, they should not cross each other. So there should be a repulsive interaction between them in such a condition. So that's which makes the interactions very difficult to calculate from an analytical point of view, but is because now we have these known local interactions present. So these are the three interactions that I just considered. I used, by the time Metropolis, Monte Carlo, could be other methods, but this is a simple one and gave very nice results. Of course, if I have just thermalized polymer on a crystalline substrate, I should recover Langevin dynamics, which means that the diffusion coefficient should go as 1/n. So from that point of view, I should not expect a change in the universality class. So, but I did very extensive simulations. Each simulations was 120 million Monte Carlo steps. Each data point was consisted of 4 of those runs, independent ones, and a data set would consist of varying the size of the monomer relatively to the size of at the substrate particle between 1.1 to 4 in steps of 0.1, a total of 39 cases. Finally, I also had to simulate for various temperatures. So I start with the higher and go to the lowest of 0.6. Most of the simulations were focused around 0.7. But I also did all the other cases. I have to just reminding that since we have the crystalline substrate, moves now do not happen automatically. They have most of the time a monomer just jiggles on its basin of attraction around the minimum where it is placed in some sense. And from time to time, it will move to some adjacent basin of attraction and become trapped there, and everything would again repeat itself. Monomers only escape from time to time. So this is the important idea. And this work was already published and on Journal Statistical Mechanics already for some time in 2017. And I just want to show what the simulations look like. For example, over here, I have a simulation at a high temperature of T equals 1, but the polymer is long enough. And what I mean by this green line that everybody's looking there, those are the bonds between, these lines are the bonds between the monomers. But if a monomer gets to be out from, say, this side, one of the sides, it re-enters from the other side. So I'm applying periodic boundary conditions, and one observes that part of the polymer is on one side of the substrate and the other is on the other side, and but there is a this green line indicating which polymers we are looking at with along the chain. So I'm going now to show a movie, and you can see that these polymers are very mobile. I'm doing frames over 100,000 steps. So they move very fast, but it is also 100,000 steps between each frame. So, every time it gets out from one side, it re-enters from the other, and sometimes multiple monomers are doing that simultaneously. So this is one case that I did by the time and showed that they are pretty mobile, even and all the time moving on the substrate without ever evaporating from it. So the results are as follows. The energy for the isotropic case, the one that scales with the size of the monomer, it basically has a parabolic behavior that is well seen in this graph around here. I just want to point out that red or open symbols are, red or filled symbols are for a size of 30, and open or blue are for a size of 60. So I have here the energy of the polymer, and it shows this parabolic behavior by the time I calculate that in terms of the area, the projection area of the monomer over the surface. So it basically reproduces the behavior. It's very well behaved, and everything was as expected. On the right side, I show on the
Antonio, sorry. What is the horizontal axis?
Which axis? Sorry.
The horizontal axis, the x-axis.
Oh, I'm sorry. I forgot that. The horizontal axis are these ratios. The ratio of the monomer, the monomer over the substrate particle, and it goes from 1 to 4 in steps of 0.1. And all the simulations were the 120 million Monte Carlo steps. I'm sorry for that. So in all these plots, the height of the polymer relatively to the substrate is basically linear, except for the very smaller ones, because it's just as it grows, the center of the monomer is basically also shifting linearly upwards. That's it. There is not much novelty around here. Everything is as expected. For example, if I calculate the diffusion coefficient, then there is, for small sizes, there is the diffusion coefficient grows rapidly for the smallest polymers, but for the largest ones, it also grows initially, but not in the same way, which is it's a larger polymer, so it's slower, it has a smaller diffusion coefficient, and it gets basically saturated not long for as the sizes of the monomers increase. The other one has a bit more of noise or possibly dependence on the size of the monomers, as we'll see. Now there is also here another third curve, lighter one, that is the simulations on the flat, smooth substrate. And these ones, they show that the influence of the crystalline surface or substrate, it's determinant in the dependence of the diffusion coefficient with gamma, in the sense that is this ratio I pointed out before. So those are size dependence on the monomer to substrate particle ratio that is quite different. So one cannot infer that size is going to be irrelevant, and the functional dependence is quite different from just picking up a flat surface. So that was a main result for the isotropic case. And now I'm going to move to the anisotropic case. So in the anisotropic case was also interesting to see, and the same happens for the isotropic case, that the diffusion coefficient as 1/n, it basically follows Rowe's regime or Langevin dynamics with very good precision. And I can see, I even have here the exponent and the error bar associated with it. Very, very good precision on that. So changing the size of the monomer relative to the substrate particle does not change the behavior of the diffusion coefficient with size of the polymer. But, on the other hand, these transitions on the right side, the diffusion coefficient as the logarithm of it as 1 over kBt. So this is Arrhenius behavior as defined in the last line, and it shows that the energies are, there is an energy barrier for transition that is given by that number. It's not the most relevant part, but the part, the relevance is that there is an activation energy barrier. That is the main point. And because now we have a crystalline substrate. So those are the cases. The colors on the right plot are also defining the sizes of the monomers, and the blue color on this side defines the temperature on the left one. But no major change with temperature was observed and I did all of those analyses, but that's basically the result for the anisotropic case. So, and also includes the isotropic one. So far, nothing very new. What was very nice to observe is that as I now look at the energy for the anisotropic case, varying the size, now there is these oscillations on the energy, and they are related also with changes in terms of the height of the polymer relatively to the substrate. And this also affected the diffusion coefficient. So all of that was a very interesting aspect, that the size will make the polymers commensurate with the substrate at some specific values. And when it was the monomer becomes well attached, then the height will be very small. And when the polymer was basically loosened, then the height will be higher, and the energies will basically have the opposite behavior, of course, because it's just a geometrical fixture. But this is a dynamical geometrical fixture. It does not reflect the polymer to be on a particular state all the time. It's observed over 120 million time steps. So all these behaviors, they have a large number of steps accumulated. So all the noise was removed from it. So as some remarks that I would like just to finish this section is to, let me see, how much time do I still have?
You have close to 12 minutes.
12 minutes? No, oh, I'm sorry. So
15 minutes.
15? Okay.
15.
So in this crystalline substrates, as you can see, the size dependence gave very nice results for the anisotropic case, but more trivial results or commonly expected for the isotropic one. So now I want to just mention, because I will not have the time, that I can include now and see the difference between how the polymer moves in this case if a single impurity or nanoparticle is present in it. And one sees that the polymer now does not move independently as before, and it is all the time attached to the impurity. Just to give an idea, and this work was just published not long ago, and the university funded the publication and so forth, and we're very grateful for that, and we thank that. But this will come at some later points that I could present something else if people think that I could do that. This is a very nice result that we obtained, because the behavior now in terms of N, the number of monomers, is quite different. And so this is a starting point for even more evolved work. And that is what makes me come to polymer and nanoparticle deposition. So for polymers and nanoparticle, this is ongoing work I'm doing with Professor Vivian, and what we are interested is using some experimental techniques to calculate how the particles are distributed on the polymeric film in the presence of some nanoparticles, and use some experimental techniques and working together with the simulations, so to compare side by side what is observed. So what is very challenging when we do growth is that we now have very different timescales for processes to taking place. Some are very fast, some are extremely excruciatingly slow. But those are the ones that will make the problem, the behavior in the long time, well defined. So those are the so-called rate determining processes. Film growth is difficult because also requires a large number of particles to obtain good statistics, long observation times due to what I just talked about, long time scales for the slowest process, and particles, they also have to move by distance that are comparable to their sizes. So any attempt to have, again, a high quality description of the potentials, it's basically computational prohibited and prohibitive, and therefore we have to think of effective representations. What in a discussion in middle of last year, we just realized that sometimes the nanoparticles, they form these aggregates. From experimental point of view, this is not the best situation. The best situations and where they are fully dispersed. So I immediately thought of a way to describe a sample that could be on this case or one that is fully dispersed, And I came up with a simple model that I call the nanoparticle deposition one, when in one case, the nanoparticles just have a repulsive interaction. So we start after even 80,000 time steps, they are homogeneously with some fluctuation present on the substrate. And after 2000 time steps, nothing basically changed. It's basically maintained that it's a fairly simple case, but a relevant one. So if they are attractive, they start far apart, but they start forming clusters. It's a very different perspective than from the repulsive case. So on the left side, the morphology is quite different from the one on the right side. So this was a very objective way to think of a model that could interact now having polymers that deposit and nanoparticles that they can or not attract between themselves, or either attract or repel each other. And there should be a very different morphology of the film in one case or the other. So I considered attractive interaction for substrate nanoparticle. They are basically all attractive. This case, the nanoparticle also attractive, and the nanoparticle monomer also attractive. Now, the monomer, they have attractive one between monomers and a repulsive one due to the bonding along the chain of the polymer. And in this case, for a short time and small number of nanoparticles and polymers, it's basically a very system that is very clean and very simple to observe. But here we can see the dynamics that is taking over in the background to obtain such a state. Very few particles, and there is not much happening. So, and also the temperature, no, this one was a high temperature. So then we start increasing the time and the number of nanoparticles and polymers. Here was more the polymers than nanoparticles, which is also closer to the experimental case. And we also have the polymer nanoparticle case, but at a higher temperature. So the temperature of the previous case is 0.5, 1/4, and now it's 3/4. So in this case, you can see a very important detail that particles, they land, they attach to the substrate, and then they can leave. And because they can leave, the roughness of the film is going to increase dramatically. And that is what I'm going to show here. So here we already see a state where roughness is already quite large. And all of that because particles can land, attach, and eventually leave the substrate. So basically there is entropic contribution due to the presence of these particles. I'm going just to start the movie. So initially, they have a very large mobility, and some of them, they start leaving the substrate after some time. There is a typical time scale for that, and this leads for other particles that when they are depositing, they will attach to those, and therefore the roughness of the film is changing over time very rapidly. So this is a very nice thing that I found out, and I'm trying to separate now the time scales when this happens and when we observe this other much nicer low temperature behavior, where everything is attached nicely to the substrate. But this is because the problem is a time-dependent problem. So there is an extra complexity associated with it. Do I still have some time? I just want to thank Professor Viviane and all the optical and thermal properties group for welcoming me to Institute, and the Institute itself even for all the support and funding that is offering over time. Thank you very much.
Thank you, Professor Cadilhe. Thank you very much for this very nice seminar. So it's open for questions now. Let me see if anyone...
I do have one question.
Yeah, so Edson, go ahead, Professor, please.
So, thank you, Cadilhe, for a very nice talk. Very pedagogic, I would say. My question actually is related to this very last part of your talk, where you include the nanoparticle. So first, do your nanoparticle has internal degrees of freedom, or they are like rigid balls? I'm asking because
they are. I'm just the nanoparticles are also in the solution, and so they are depositing from the solution. In this case, I'm still considering some the number of nanoparticles relatively to the polymer are still too high for an experimental point of view. The interest is on smaller concentrations, so smaller probability from them to attach to the substrate. On the other hand, I'm using them in an effective way. So they are very large, but they will, I'm looking for systems that are very, very large. So their size, the details of interaction, that they can or not move on the substrate, and the time scales are not that relevant. As far as I see that the competing time scales between them and the polymers, those are the most relevant ones. And also the time scale that they can detach from the substrate. So those are the real time scales that are more fundamental. The actual shape of the nanoparticle in this case is, I don't think is that relevant, at least at this point. I'm not sure that there is a big relevance for the largest systems. But of course, If I wanted to be more careful with the interactions for short than 4 times, then I have to take that into account.
Yeah, because I was thinking if the nanoparticle collides between themselves, so they would tend to clusterize and form some cluster of nanoparticle, but this doesn't happen, right?
Yes. But that was also, they have these clusters or some clumps of nanoparticles, because I'm also considering a density of them too high for the experimental.
Okay.
So if I lower that, the chances that they will be separated are much larger. Those are still this is still ongoing work, and I'm still looking for the time scales that I will get from the experimental side, but in order to compare the magnitudes of the time scales. So I can then, after that, to see if I should basically put how much time between the positions of nanoparticles and the positions for the polymers.
Okay,
the
thank you.
position time.
Thank you.
I have a couple of questions. One of them is you mentioned two different types of models, the isotropic and the anisotropic. I assume that one models one polymer better and the other models another kind of polymer better, or
yes, a three-dimensional one. One that is basically, say, a ring would basically have more of what I call the isotropic behavior. Because it's flat, it will attach along the substrates to maximize coordination, and therefore it would be more of this type.
okay.
On the other hand, typically these bonds are covalent ones, so they are pretty much directional, and it can have a three-dimensional behavior. So only a few points, and I consider it the extreme case of one. Having two or three would add to an understanding of a particular problem, but not the general behavior of the polymer. So that's why I considered just one to make everything simple, but keeping the main argument that is not going to interact with a number of particles proportional to its size. And so there are very few particles now interacting with the substrate for each monomer. Okay. And this leads to this type of behavior that now has some special sizes of the ratio that either favor attachment to the substrate or not.
Okay.
And this is because it's a crystalline substrate.
Okay. The other question is we always, when we try to sell our projects to the funding agencies, we try to this can be applied to this or can be applied to that. This specifically, you mentioned silver nanoparticles and this polymer specifically ketosene. Why are those the ones that you chose and Professor Viviani too chose to study? Is there any application or is that
yes, they have applications as for what they form is a matrix of polymers with these nanoparticles present in it. And this can be used for all radiation detectors and so forth.
Okay.
That is very important from a application point of view.
So the idea is to study the best way to grow these films, right? What are the parameters, temperature, concentrations, and everything? You are trying to simulate the ideal way of growing these films. Okay.
That is, hopefully, it can be one step further. At this point is exactly that, but the next step would be how the material, let's say the nanoparticle is the part that is more, the more interesting part from a optical perspective is how the sample is going to behave in terms of optically by the morphology that the nanoparticles form on the film.
Okay.
So the matrix of nanoparticles in this polymeric film is going to have some correlations, special correlations that will influence optical properties.
Okay, so the polymers are optically transparent. The idea is that they won't influence the properties of the nanoparticles.
They will also have some contribution, but the important part is to decouple the two contributions and focus on the nanoparticles or the polymers.
Okay, okay. Okay, so let's see if we have more questions. I think, and
I do have one more.
Edison, please go ahead.
This is all the simulation is classical, right, as far as I understand. So
yes.
So have you had a chance to look at the distribution, the velocity distribution of this nanoparticle, or even in for the polymer? So if so, does it follow the Maxwell-Boltzmann distribution function, or there's something different?
No. The problem is the following. Let me point out here. I'm just looking for the nanoparticle, but it could be also with the polymer. I'm talking about very large times. So the motion here is basically one of a nanoparticle jiggling on the surface of the substrate until eventually it falls on a neighboring position. So they are not moving at the kinetic energy of these systems. It's just basically thermal one. So with very little impact on the overall. This is for the case of attractive interaction. It started initially with some clumps, some aggregates, but over time, just because it's attractive, in this case, they keep annealing and growing this. They will not grow indefinitely if I were to have a very large substrate, because the temperature is fixed and some will leave the substrate, some they will move along the substrate from one aggregate to another. So everything is possible in these simulations. So that's why they, in a sense, it's complicated what is happening on this sort of system.
Thank you.
I have one more question. Is the substrate inert, or you try to use a specific substrate that will help the growth of the film? In that case, what substrate is that?
The substrate, I basically froze it just to remove moving particles, which decreases the simulation by the number of particles. There will be a difference, definitely, just if the substrate is also thermalized and active. But in a sense, I'm once again is thinking of effective behavior, and that effective behavior is not expected to change, say, that aggregates will grow or not. It just basically could change some mean size, some rates, but not, say, the overall behavior of the system.
Okay.
That is the most important aspect. It cannot change the physics, but it's not the same physics, but it's equivalent one. Okay. I'm not losing relevance.
Okay. Well, if we don't have Edson, any more questions?
No, I'm good. Okay. So I had to apologize because my son is making a lot of noise behind here. So I could reduce a lot of disturbance. You can see.
He's a very happy child. He's a very happy.
I can next time I let him to make questions.
Okay. So if there are no more questions, we should thank the speaker again. Thank you very much for the very nice seminar. I will be asking you by email to send if you may, if it's possible for you to send us the slides so we can post together with the video in our YouTube channel.
Okay.